Hi students, today I am going to discuss about the second unit of the subject Electronic Circuits 2. The title of the second unit is Oscillators. So in the first unit, that is in the previous unit, we discussed about the feedback amplifiers. So what is meant by feedback amplifier and what are the types of feedback amplifier and what are the concepts of series shunt amplifiers. So in the second unit, I am going to discuss about the concept oscillator. So first of all, what is meant by oscillator? Oscillator is the electronic circuit which gives output signal without any external input. That is, for an oscillator, there is no need for giving the input. And the very important, it is a circuit which produces a continuous waveforms on its output with only the DC supply voltage as an input. So the only input is called as DC supply voltage. Okay, there is no external input to the oscillator, and the oscillator converts the DC power supply to the AC power in the load. So it is the reverse concept of the rectifier, just opposite to the rectifier. And here the oscillator, the output voltage can be either sinusoidal or non-sinusoidal waveform. So it's depend upon the type of oscillator. So this unit fully focuses about sinusoidal oscillators only. And now you can see the difference. So what are the difference between the amplifier and the oscillator? For the amplifier there is a finite gain, and for the oscillator there is infinite gain. And the next point, in the amplifier the output frequency waveform and the magnitude of the signals are controlled by the AC input, because for the amplifier we should give the input actually, but for the oscillator it can controlled by the circuit itself. That is the second difference. And the amplifier which uses the negative feedback, but the oscillator uses the positive feedback. And now you are seeing the schematic diagram of the amplifier and the oscillator. Just see the amplifier diagram. In this amplifier, here we should given the input as signal and the second DC power input, and it shows the output signal. For the oscillator there is no input. Okay, so directly gives the output signal based upon the DC power input, so which produces sinusoidal waveform as well as non-sinusoidal waveforms. Next classification of oscillator. So the major classifications are: the first one, sinusoidal oscillators, or it is called as harmonic oscillator. The second type, non-sinusoidal oscillators or relaxation oscillators. Okay, non-sinusoidal waveforms is nothing but a square waveform, triangular, ramp, staircase waveform, etc. And now we can discuss about the basic principles of sinusoidal oscillators. So before going to the topic, we should recall about the first unit. Okay, in the first unit we already studied about what is meant by gain, what is gain with feedback, and what is meant by gain without feedback, right? So now you can see the diagram. So this diagram shows three components, right? The first component is nothing but as mixer network. That is what this summation symbol, it is called as mixer network. The second network is called as the amplifier network, and the third network can be called as beta. So beta is nothing but as feedback network. Okay, now this diagram shows the first input as xs, that is what source input. Here the term x, okay, the x, it can be either voltage or current. Okay, so commonly I can use the term as x. Okay, so xs is the source input, xi is the input signal, and x naught is the output. Okay, it may be a voltage or current. And here the part of the output can be given to the network feedback network, that is what beta. Okay, a part of the output, that is a sampling. By using the sampling network we can give it the part of the signal to the feedback network, and this xf is the feedback factor or feedback ratio. So this is the explanation of this circuit. And here, so it is the oscillator, so we should use this the positive feedback. So positive feedback is nothing but as, here there is a positive sign and here there is a, again is a positive sign. But for the amplifier we can use negative feedback. So here in the first, in xx we use the positive sign, and here we can use the negative sign. But for the oscillator we can use both positive signs. So here, so we can see that explanation. In an actual oscillator circuit, no input signal will be present, as we already explained. So the feedback is said to be the positive whenever the part of the output, that is feedback to the amplifier as its inputs, is in phase with original input signal. Okay, both are in same phase. That is what positive and positive. Let us assume that an input signal is xs. So I explain now, xs is the input signal or source input, and again this xa is the input of the amplifier, and x naught is the output of the amplifier, and this xf is the feedback network or feedback ratio or feedback of the feedback signal of the feedback network. And now you can see the expression. So first, by using the circuit diagram, you can see the open loop gain expression. Okay, what is open loop gain? That is what A. So A is nothing but as transfer gain. Okay, so here we can closed loop line can be called as AF. So what is the difference between this A and AF? So A is nothing but as gain without feedback, and AF is gain with feedback. So the open loop gain can be called as A equal to x naught by xi. So the open loop gain is what? This x naught, this x naught by xi. Okay, the closed loop gain can be called as x naught by xs. Closed loop gain can be called as x naught by xs. That is what AF, gain with feedback. And now the feedback xf, when added with xs, it generates the part of the amplifier. That is what, so we can write xi equal to xs plus xf. Okay, I already mentioned, now we are using both are in same phase, so there is a positive sign. So xi equal to xs plus xf, because the mixer network which adds the two signal. Okay, for the mixer we have two input, the first input is xs and the next input is xf. So the mixer which adds the two signal xi equal to xs plus xf. Okay, now I can write xf equal to beta into x naught, xf equal to beta into x naught, and this is the fourth equation, and xi equal to xs plus xf is the third equation. Now I am going to substitute this fourth equation in the third one. Okay, so xi equal to xs plus beta into x naught. So in this equation I am going to rewrite xs equal to xi minus beta into x naught. So this is what the sixth equation. So now I am going to substitute this sixth equation in the second one. So second one is AF equal to x naught by xs. Okay, so AF equal to x naught by, so xs equal to xi minus beta into x naught, and this is the seventh equation. And in this equation I am going to divide the term xi in both numerator and denominator. Okay, so AF equal to x naught by xi by xi by xi minus beta into x naught by xi. Okay, so as we already know, x naught by xi equal to A, that is open loop gain, and xi by xi is 1, and beta into x naught by xi can be called as again A. So the final gain with feedback equation can be given as AF equal to A by 1 minus A into beta. So here this equation represents the oscillator which uses the positive feedback. In case for the amplifier, the same equation can be written as AF equal to A by 1 plus A beta. That is the equation for amplifier. But for oscillator, the gain with feedback is equal to A by 1 minus A beta. And the next topic, next we are going to discuss about an important topic is called as Barkhausen criterion. It's a very important 2-mark question. So they will ask like state Barkhausen criterion or write the conditions of Barkhausen criterion. Okay, so please listen it carefully. And yes, this is the basic block diagram of the oscillator. And again, this diagram which shows us the basic inverting amplifier and feedback network, and we are giving the input as xi, and x naught is the output of the inverting amplifier. Now I will give the part of the output can be given to the feedback network. So the feedback network can be given as beta. So xf equal to beta into x naught, beta into x naught. And now this diagram which shows it can produces a 360-degree phase shift, because the amplifier which produces 180-degree phase shift, and with addition of this feedback network produces the again 180-degree phase shift. So totally 180 plus 180. So this circuit which produces 360-degree phase shift. And now let us see that expression. So consider voltage xi applied to the input of the amplifier. So here x naught equal to xi into A. So A is nothing but as gain of the inverting amplifier. X naught equal to A into xi. The feedback factor beta decides the feedback to be given to input. So the feedback network, yeah, this xf equal to minus beta into x naught. So the minus sign, the negative sign, this negative sign indicates the 180-degree phase shift. Okay, that is what here xf equal to minus beta into x naught. Now I am going to substitute this second equation in the first equation. So sorry, first equation in the second equation. So xf equal to minus a beta into xi. So this is the third equation. So now for the oscillator, the feedback drives the amplifier. That is what the XF. So the feedback gain must be act as Xi, input signal. So XF equal to Xi. Now I am going to substitute XF equal to Xi. So Xi equal to minus A beta into Xi. So this Xi and this Xi will be cancelled. So minus A beta equal to 1. So minus A beta equal to 1, and this is the first important condition of Barkhausen criterion. Okay. So now I am going to taking the magnitude of this equation, modulus of A beta equal to modulus of minus 1 plus J0. So real part plus imaginary part, that is modulus of A beta equal to 1. So this is the very first important condition of Barkhausen criterion. Okay. So this XF must be same as Xi, that is the feedback network should introduces 180-degree phase shift with addition to 180-degree phase shift introduced by the amplifier. So the total phase shift can be given as 360 degree, and this is the second important condition of Barkhausen criterion. Okay, the first condition is modulus of A beta equal to 1. That is what the product of gain with feedback can be given as 1. The second condition is the total phase shift of the circuit can be given as 360 degree. Yes. Now again we can see the condition of the Barkhausen criterion. Yeah, it's an important 2-mark question. So the first condition is the total phase shift around the loop is accurately or precisely 0 degree or 360 degree. The second condition is the magnitude of the product of the open loop gain A, the amplifier, and feedback factor beta is unity. So A is nothing but as the open loop gain of the amplifier, and beta is nothing but as the feedback factor or feedback ratio. It is given as 1. Okay. Now we can discuss about the types of oscillations. Okay, what are types of oscillations based upon the conditions? The first condition, if A beta is greater than 1. Okay, so what will happen if A beta is greater than 1? So when the total phase shift around the loop is 0 degree or 360 degree, and the output should like this type of output. So okay, this output shows the oscillations are of growing type. Okay, you can see the diagram. The oscillations are growing. So it's what it's keep on growing. So it is called as the first condition. A beta is greater than 1. The second condition, A beta is equal to 1. So here the oscillations are with constant frequency and amplitude. Okay, so this is called as sustained oscillation. Now you can see the graph. This graph shows the constant amplitude with constant frequency, and this is called as sustained oscillation. And when the condition is what? A beta equal to 1. And the third condition, A beta is less than 1. Okay, so what will happen if the A beta is less than 1 is, so the oscillation is decreases exponentially. Okay, you can see the oscillation which was decreases exponentially. So that is what the condition, A beta is less than 1. So if you want to get the clear output, if you want to get the exact output, means you can set the oscillation A beta equal to 1. So you can see to start the oscillations without input, A beta is greater than 1, and we have to circuit the adjust the value A beta equal to 1. So if A beta equal to 1 means it can produces the sustained oscillations. And next we can see about what are types of oscillators in our second unit. So as I told before, the overall types are sinusoidal, first one. The second one is non-sinusoidal oscillators or relaxation oscillators. So here let us see the frequency range of the oscillator. The first, the audio frequency oscillators, the range can be given as hertz to some 20 kilohertz, and for radio frequency oscillator 20 kilohertz to 30 megahertz, and for very high frequency oscillators 30 megahertz to 300 megahertz, ultra high frequency oscillator 30 megahertz to 3 gigahertz, and for microwave oscillators the range can be given as 3 gigahertz to several gigahertz. Okay, and yes, in our second unit, we only focuses about the sinusoidal oscillators, not non-sinusoidal oscillators. Okay, so in our syllabus, as per the syllabus, we are going to discuss about only the sinusoidal oscillators. So now we are seeing the types. The first one is called as LC oscillators. So LC oscillators is nothing but as tuned circuits. Okay, as the name suggests, LC. So this oscillator have inductor and capacitors. Okay, the types of LC oscillators are Hartley oscillator, Colpit oscillator, Clap oscillator, Armstrong oscillator, Franklin oscillator, and finally tuned collector oscillator. The next type is RC phase shift oscillator. Okay, so RC is nothing but as it have the components like resistor and capacitor. The types of RC oscillators are given as RC phase shift, Weinbridge, and twin T oscillators. And finally, the last type is crystal oscillators. In crystal oscillators, we have only two types. The one is Pierce crystal and Miller crystal oscillators. Thank you.